A very good morning, friends. I welcome you all for the last session of the first chapter, that is combinational logic circuits. So far in the previous session, we have seen the concept of encoders. Encoders are the one. So encoders are the combinational logic circuits. So which receives the decoded information on 2 to the power of n input lines, and it produces an encoded data on n output lines. Now there is a problem. There is a problem with the standard encoder. So before introducing the priority encoder, let us discuss what is the problem with the standard encoder. Let us consider an example. So as we have already seen the 4:2 encoder operation. So here, so it consists of 4 input lines and 2 output lines. This 4:2 encoder, it receives information, the decoded information on 4 input lines, and produces the encoded output on the 2 output lines. The decoded information, in the sense, out of these 4 input lines, any one input line will be active high. So depending upon which input line is active high, corresponding to that, an encoded output will be produced on the 2 output lines. As you can see from the truth table, in the first combination, y0 is only 1 or active high, rest all input lines are 0. Corresponding to this y0, an encoded output will be 0 0. Similarly, in the second case, y1 is only active high and rest all input lines are zeros. That's why it produces an encoded output as 0 1. Similarly, if you go through the last combination, y3 is only 1 and rest all input lines are zeros. That's why it produces an encoded output 1 1 on the output lines. Let us consider a situation where more than one input lines are active high. So let's say in the first combination only y0, it was 1, that's why it produces an output 0 0. Let us consider even y1 is also 1, y2 is also 1, and y3 is also 1. In such a situation, the normal encoder, it fails to detect which input line it has to consider, because there are more than one inputs are at logic high level. So then the output that is produced, that is 0 0, it is an invalid one. Let us consider this with a real example. Let us say if the teacher asks a question among the 10 students, if only one student raises his hand to answer the question, then obviously a teacher is going to ask the student, whoever has raised his hand, and he is going to answer. That is all okay. Let's say if there are two students simultaneously raises their hands, means a teacher will get confused to whom he has to address his question. In such a situation, normally the teacher, he is going to assign the priority to the students. He might have his own priority levels that he has assigned to the students. ಅಂದ್ರೆ ಲೆಕ್ಚರರ್ ಕ್ವಶನ್ ಕೇಳಿದಾಗ ಮೋರ್ ದೆನ್ ಒನ್ ಸ್ಟೂಡೆಂಟ್ಸು ಹ್ಯಾಂಡ್ ರೈಸ್ ಮಾಡಿದ್ರೆ ಅವಾಗ ಅವರು ಯಾರಿಗಾದ್ರೂ ಒಬ್ರಿಗೆ ಕೇಳಬೇಕು. ಯಾರಿಗೆ ಫಸ್ಟ್ ಕೇಳಬೇಕು, ಅದು ಪ್ರಿಯಾರಿಟಿ ಬೇಸಿಸ್ ಮೇಲೆ ಕೇಳಬೇಕಾಗತ್ತೆ. ಪ್ರಿಯಾರಿಟಿ ಅಂದ್ರೆ ಯಾರಿಗೆ ಫಸ್ಟ್ ಪ್ರಿಫರೆನ್ಸ್ ಕೊಡಬೇಕು, ಯಾರಿಗೆ ನೆಕ್ಸ್ಟ್ ಪ್ರಿಫರೆನ್ಸ್ ಕೊಡಬೇಕು, ಯಾರಾದರೂ ಒಬ್ಬರಿಗೆ ಮಾತ್ರ ಕೇಳಬೇಕು. So in such a situation, whenever more than one input lines are at active high levels, the normal standard encoder, it fails to predict the output. In such a situation, we need a special kind of encoder which is going to assign the priorities to the inputs. Let's say ನೀವು ಒಬ್ರು ಲೆಕ್ಚರರು ಯೂಸಲಿ ಲೇಡೀಸ್ಗೆ ಫಸ್ಟ್ ಪ್ರಿಫರೆನ್ಸ್ ಕೊಟ್ಟು ಜೆಂಟ್ಸ್ಗೆ ಸೆಕೆಂಡ್ ಪ್ರಿಫರೆನ್ಸ್ ಕೊಟ್ಟಾಗ ಒಬ್ಬ ಹುಡುಗಿ ಇಬ್ರು ತಮ್ಮ ಕೈನ ರೈಸ್ ಮಾಡಿದಾಗ ಆನ್ಸರ್ ಮಾಡಲಿಕ್ಕೆ ಲೆಕ್ಚರರು ಫಸ್ಟು ಲೇಡೀಸಿಗೆ ಕೇಳ್ಬೋದು. ಅವ್ರು ಆನ್ಸರ್ ಮಾಡಿದಾದ್ಮೇಲೆ he can assign the next priority to the boys. ಸೊ ಆಮೇಲೆ ಹುಡುಗರಿಗೆ ಕೇಳ್ಬೋದು. ಅಂದ್ರೆ teacher, he has assigned his own priority levels among the students. Similarly, in order to assign priorities among the input lines, whenever there are more than one inputs are at active high levels, then we use a special kind of encoder which is known as priority encoder. So this is the encoder which is going to assign the priorities among the inputs available. So whichever it is going to produce the output corresponding to the inputs, whichever has got the highest priority. Okay, so the same thing is discussed here. The main disadvantage of standard digital encoder is that it can generate wrong output whenever there are more than one input present at logic 1 level. To overcome this problem, ಈ ಪ್ರಾಬ್ಲಮ್ ನ ಓವರ್ಕಮ್ ಮಾಡಲಿಕ್ಕೆ a special type of encoder is introduced which is known as priority encoder. How it works? The priority encoder is going to assign a priority levels among their inputs. In priority encoder, if two or more inputs are at logic 1 level at the same time, then the input having highest priority will take the precedence. ಅಂದ್ರೆ ಯಾವುದಕ್ಕೆ ಹೈಯೆಸ್ಟ್ ಪ್ರಿಯಾರಿಟಿ ಕೊಟ್ಟಿರ್ತಾರ ಅದಕ್ಕೆ ಕರೆಸ್ಪಾಂಡಿಂಗ್ ಆಗಿ ಔಟ್ಪುಟ್ ನ ಪ್ರೊಡ್ಯೂಸ್ ಮಾಡುತ್ತೆ. ಲೆಟ್ಸ್ ಸಿ ದ ಆಪರೇಷನ್ ವಿತ್ an example. A 4-bit priority encoder which has got 4 inputs D0, D1, D2 and D3. So among these 4 inputs, D0 is considered as the LSB bit and D3 is considered as the MSB bit. So here this priority encoder, it is going to assign the highest priority to the D3 and very lowest priority to the D0. The priority level, it decreases in this fashion. The highest priority is given to D3, followed by D2, followed by D1, and at the last the lowest priority is given to D0. If all these inputs are 1 means, then the output is produced corresponding to the bit which has got the highest priority, that is corresponding to the D3. It is going to produce an output 1 1. It is going to neglect the input bits which have got the low priorities. It will consider andra D3 will take the precedence here. Okay, here in this logic system there will be 3 outputs. As it is a 4:2 encoder, normally 2 outputs will be there which are designated with the letters Y0 and Y1. There is one more additional output which is going to indicate the validity of the output. So whether the output is valid or not. In order to check that, there is one more output is there, that which is designated with the letter V. Let's see the logic symbol first. You can see the logic symbol here. It has got 4 inputs. It is normally a 4:2 encoder, but it is a 4:2 priority encoder. It has got 4 inputs D0, D1, D2 and D3, and there are 3 outputs Y0 and Y1. These are the regular outputs, and one more new output is introduced, which is nothing but V, which is going to indicate the validity of the output. Let's see the operation with the truth table. So in the truth table, D0, D1, D2, D3, these are the inputs, and Y0, Y1, Y0, and V, these are the outputs. Let's say if all inputs are zeros, very first case is if all inputs are zeros. So none of the inputs are at active high level means then there won't be a proper output, and we neglect the output and output won't be valid. That's why the V output bit will be 0. Whenever V is 0, it indicates the output is invalid. The same thing is written here. V is 0. If V is equal to 0, that indicates it is an invalid output. Now let us consider in the second case, D0 is 1, D0 is 1, and rest all inputs are zeros, means D1, D2 and D3 bits are zeros. As we know that the MSB bit D3 has got the highest priority, and D3 has got the lowest priority. Actually, this is written in the reverse order. Please make a correction here. This bit should be D3, and this one is D2, and this one is D1, and this one is D0. Okay, D0 has got the lowest priority and D3 has got the highest priority. The priority function plays into role whenever more than one inputs are at active high level. But in the first case, only D0 is 1, rest all inputs are zeros, means D0 will get the highest priority. According to this, the output will be 0, 0. Corresponding to this decimal digit 0, the output will be 0, 0. In the next case, D1 is 1, whereas D2 and D3 are 0, zeros. So in this case, since D1 is 1 means, if you compare D0 and D1, D1 has got the higher priority compared to D0. Means even though D0 is 0 or D0 is 1, so that's why we are written here don't care condition. It means irrespective of the value of D0, whether it is 0 or 1, D1 will take the precedence. So according to this decimal digit 1, the output will be 0, 1, and again this is a valid output. Similarly, in the third case, a D2 bit is 1, D2 bit is 1, and since the D2 bit has got the higher priority level compared to D1 and D0, so irrespective of the values of D0 and D1, whether they may be 0 or 1, a D2 will take the precedence, and according to this, the output will be corresponding to this, the output will be 1, 0. Again, this is a valid output. Similarly, in the last case, D3 bit is 1. So whenever D3 bit is 1 means, since the D3 has got the highest priority, so irrespective of the uh, input bits that are D0, D1 and D2, whether they are 1 or zeros, D3 will take the precedence. So that's why the output will be 1, 1. ಅಂದ್ರೆ ಇಲ್ಲಿ ಲಾಸ್ಟ್ ಕಂಡೀಷನ್ ಅಲ್ಲಿ ನೋಡಬಹುದು D3 1 ಇದ್ದಾಗ D3 ಹೈಯೆಸ್ಟ್ ಪ್ರಿಯಾರಿಟಿ ಕೊಟ್ಟಿರ್ತೀರಿ. ಸೊ D3 1 ಇದ್ದಾಗ ಸೊ D2 D1 D0 ಏನಾರ ಇರಲಿ 1 ಇರಲಿ ಅಥವಾ 0 ಇರಲಿ, ಲೆಟ್ ಅಸ್ ಕನ್ಸಿಡರ್ ಇವೆಲ್ಲಾನು 1 ಅದಾವ ಅಂತ ತಿಳ್ಕೊಳ್ಳೋಣ. ಸೊ ಎಲ್ಲಾನು 1 ಇದ್ರೆ ನಾರ್ಮಲ್ ಎನ್ಕೋಡರ್ ಏನ್ ಮಾಡುತ್ತೆ, ಇಟ್ ವಿಲ್ ಗೆಟ್ ಕನ್ಫ್ಯೂಸ್ಡ್ ಬಿಕಾಸ್ ನಾರ್ಮಲ್ ಎನ್ಕೋಡರ್ produces output corresponding to the inputs, ಅಂದ್ರೆ out of many inputs corresponding to the input level whichever has got the logic high state, corresponding to that output will be produced. But ಇಲ್ಲಿ more than one inputs active ಆಗಿರೋದ್ರಿಂದ ನಾರ್ಮಲ್ ಎನ್ಕೋಡರ್ ಸರಿಯಾಗಿ ವರ್ಕ್ ಆಗಂಗಿಲ್ಲ, ಔಟ್ಪುಟ್ ವ್ಯಾಲಿಡ್ ಔಟ್ಪುಟ್ ಕೊಡಲ್ಲ, ಅದು ಇನ್ವ್ಯಾಲಿಡ್ ಔಟ್ಪುಟ್ ಕೊಡುತ್ತೆ. ಸೊ ಆ ಟೈಮ್ನಲ್ಲಿ ಸೊ ಪ್ರಿಯಾರಿಟಿ ಎನ್ಕೋಡರ್ ಯೂಸ್ ಮಾಡಿದಾಗ ಸೊ D3ಗೆ ಹೈಯೆಸ್ಟ್ ಪ್ರಿಯಾರಿಟಿ ಇರೋದ್ರಿಂದ ಕರೆಸ್ಪಾಂಡಿಂಗ್ ಟು D3 ಬಿಟ್ ಔಟ್ಪುಟ್ ಏನ್ ಬರುತ್ತೆ 1, 1 ಅಂತ ಬರುತ್ತೆ. ಸೊ ಅಗೇನ್ ದಿಸ್ ಇಸ್ ಅನ್ ವ್ಯಾಲಿಡ್ ಔಟ್ಪುಟ್. ಸೊ ಲೈಕ್ ದಿಸ್ priority encoder, so it works on the priority function. So priority function andre it will assign the priority levels to the inputs, and whichever input has got the highest priority, according to that output will be produced. ಫಸ್ಟ್ನೇ ಕೇಸ್ನಲ್ಲಿ ಎಲ್ಲಾನು ಜೀರೋ ಇದಾವ, ಸೊ ಅದಕ್ಕೆ ಎಲ್ಲಾನು ಜೀರೋ ಇರೋದ್ರಿಂದ ಇದು ಇನ್ವ್ಯಾಲಿಡ್ ಔಟ್ಪುಟ್ ಆಗುತ್ತೆ. ಸೊ ಸೆಕೆಂಡ್ ಕೇಸ್ನಲ್ಲಿ ಡಿ ನಾಟ್ ಮಾತ್ರ ಒನ್ ಇದ್ದು ಉಳಿದಿದ್ದೆಲ್ಲ ಏನದಾವೆ ಜೀರೋ ಅದಾವ. ಸೊ ಡಿ ನಾಟ್ ಮಾತ್ರ ಒನ್ ಇರೋದ್ರಿಂದ ಇಲ್ಲಿ ಮಿಕ್ಕಿದ ಬಿಟ್ಟೆಲ್ಲ ಹೈಯರ್ ಪ್ರಿಯಾರಿಟಿ ಬಿಟ್ಸ್ಗಳು ಏನದಾವೆ ಜೀರೋ ಇರೋದ್ರಿಂದ ಡಿ ನಾಟ್ಗೆ ಕರೆಸ್ಪಾಂಡಿಂಗ್ ಜೀರೋ ಜೀರೋ ಅಂತ ಬಂತು. ಥರ್ಡ್ ಕೇಸ್ನಲ್ಲಿ ಡಿ ಒನ್ ಇದ್ದು ಡಿ2 ಡಿ3 ಜೀರೋ ಇದ್ದಾವೆ. ಡಿ ನಾಟ್ ಅವಾಗ ಜೀರೋರ ಇರಲಿ ಅಥವಾ ಒನ್ನರ ಇರಲಿ ಡಿ ಒನ್ಗೆ ಹೈಯೆಸ್ಟ್ ಪ್ರಿಯಾರಿಟಿ ಇರೋದ್ರಿಂದ ಹೈಯರ್ ಪ್ರಿಯಾರಿಟಿ ದೆನ್ ಡಿ ನಾಟ್ ಇರೋದ್ರಿಂದ ಸೊ ಡಿ ಒನ್ಗೆ ಕರೆಸ್ಪಾಂಡಿಂಗ್ ಆಗಿ 0 1 ಅಂತ ಬರುತ್ತೆ. ಸಿಮಿಲರ್ಲಿ 1 0 ಅಂಡ್ ದ ಲಾಸ್ಟ್ ಒನ್ ಇಸ್ 1 1. And this is the logic diagram for a 4-bit priority encoder. This is an important question in your examination. You have to write the background first, why the priority encoder is introduced. Then you have to illustrate the priority encoder with an example. Normally a 4-bit priority encoder is standard priority encoder is illustrated with its logic symbol and truth table. You have to give the explanation. And here in the truth table, v equal to 1 it indicates it is an valid output, v equal to 0 it indicates an invalid output, and x you already know this is a don't care condition, in the sense it may be 0 or it may be 1. Okay, next, the difference between decoder and encoder. This is again an important question for 5 marks. So in decoder, one of the output lines is activated corresponding to the binary input. In case of encoder, standard encoder, output lines generate binary code corresponding to the input value. Means these will work in the reverse way, exactly in the reverse way. Input of the decoder is an encoded information presented on n inputs and producing 2 to the power of n possible outputs. And in case of encoder, so it will receive the decoded information that is presented on 2 to the power of n inputs and produces an encoded data on the n possible output lines. Normally, in case of decoder, as you know, the decoder is indicated by n is to 2 to the power of n, and this is indicated by 2 to the power of n is to n. Means input lines are generally here less than outputs, whereas in case of conversely, in the case of encoder, number of input lines will be more than the number of outputs. Then we give some standard examples, that is 2:4 decoder and 3:8 decoder, whereas in case of encoder, a 4:2 or 8:3 encoder can be given as an example. And these are the logic symbols, so which will illustrate the decoder system as well as encoder system. Okay, so this completes the decoder and encoder concepts. Next we shall see, so this one we have already discussed while discussing the applications of the multiplexers. Usually the multiplexers are used to implement the logic gates as well as the logic expressions, that is SOP. SOP means sum of products. We will follow some steps while implementing any kind of logical expressions using multiplexers. Very first step is the Boolean expression is simplified using Boolean laws to obtain a canonical SOP form. What is this canonical SOP form? Normally, an SOP is nothing but sum of products. Means it is an expression which consists of many products which are added together. Then what is canonical SOP form? Canonical SOP form andre ಏನಪ್ಪಾ ಅಂದ್ರೆ, we expect all the literals to be included in all products. For example, if I write y equal to AB plus AC, this is a logical expression. This is not in the canonical SOP equation. No doubt it is an SOP only, SOP equation, because there are two products are there and these two are added. This is an SOP equation, but this is not in the canonical SOP form. Canonical SOP form andre ಏನಾಗುತ್ತೆ? First we have to see how many different literals are there. How many different variables are there? There are totally 3 variables are there. ಯಾವ್ಯಾವಪ್ಪ? A, B and C. But if you see the first product, there is a literal which is missing. ಯಾವುದು? C ಅಂತ missing ಇರುತ್ತೆ. Similarly, if you see the second product, here another literal, that is B, is missing here. If all literals are included in the products, then only it can be called as a canonical SOP equation. So canonical form nag irlillappa andre first step appa andre ಏನಪ್ಪ ಅಂದ್ರೆ you have to convert it into a canonical SOP form. So canonical SOP form andre you have to make sure that all literals are included in the product, then only that equation or that form can be known as canonical SOP form. We will see how to obtain a canonical SOP form in the next slide. Once we get the canonical SOP equation, next thing is, if we have n variables, we take all the n variables and connect them to the select lines of the multiplexer. If there are, you can see here, there are 3 variables are here, A, B and C. Then we should see for a multiplexer for which the number of literals in the canonical SOP equation are equal to their number of selection lines in them. Since there are 3 literals or 3 variables in here, then we should look for a multiplexers. We should look in the multiplexers who have got the 3 selection lines. 3 selection lines ಇರುವಂತ multiplexer ಯಾವುದು? That is a multiplexer 8:1. So that 8:1 multiplexer has got 3 selection lines. You have to select a proper multiplexer. ಹೆಂಗಪ್ಪ selection ಮಾಡೋದು? You have to count the number of variables. ಎಷ್ಟು ವೇರಿಯೇಬಲ್ಸ್ ಅದಾವ ಅದನ್ನ ನೋಡ್ಕೊಂಡು ಅಷ್ಟೇ ಸೆಲೆಕ್ಷನ್ ಲೈನ್ಸ್ ಇರುವಂತ ಮಲ್ಟಿಪ್ಲೆಕ್ಸರ್ ನ ಚೂಸ್ ಮಾಡಬೇಕು. ದಟ್ ಇಸ್ ದ ಸೆಕೆಂಡ್ ಸ್ಟೆಪ್. ಇನ್ ದ ಥರ್ಡ್ ಸ್ಟೆಪ್, as per the min terms, the corresponding mux inputs are connected to VCC. ಅಂದ್ರೆ what are these products are written for? Products, they indicate the combinations of the inputs for which the output is 1. ಅಂದ್ರೆ products SOP equation ಬರೆದಾಗ ನಿಮಗೆ ಏನು ಸಿಗುತ್ತೆ? You will get different products which are added together. ಆ ಪ್ರಾಡಕ್ಟ್ಸ್ ಏನು ಇಂಡಿಕೇಟ್ ಮಾಡ್ತವೆ? The products, they indicate the combination. ಯಾವ ಕಾಂಬಿನೇಷನ್ಗೆ, ಇನ್ಪುಟ್ ಕಾಂಬಿನೇಷನ್ಗೆ ಔಟ್ಪುಟ್ 1 ಇರುತ್ತೋ ಆ ಕಾಂಬಿನೇಷನ್ ಅದನ್ನ ರೀಪ್ರೆಸೆಂಟ್ ಮಾಡಲಿಕ್ಕೆ ನಾವು ಪ್ರಾಡಕ್ಟ್ ಟರ್ಮ್ಸ್ ನ ಬರೆದಿರ್ತೀವಿ. ಅಂತ ಪ್ರಾಡಕ್ಟ್ಸ್ ನ ನಾವೇನ್ ಮಾಡಬೇಕಾಗತ್ತೆ? ಅಂತ ಪ್ರಾಡಕ್ಟ್ ಕಾಂಬಿನೇಷನ್ ನ ನಾವು VCC ಗೆ ಕನೆಕ್ಟ್ ಮಾಡಬೇಕಾಗತ್ತೆ. ಮಿಕ್ಕಿದ್ದೆಲ್ಲಾನು ಗ್ರೌಂಡ್ ಗೆ ಕನೆಕ್ಟ್ ಮಾಡಬೇಕು. ದಟ್ ಇಸ್ ಯುವರ್ fourth step. We will see all these steps one by one whenever we discuss with an example. Let's see an example first. Okay, so here they have given an example: a bar b plus b bar c bar plus abc. What is the first step? Very first step is to obtain the logic expression or the boolean expression in canonical SOP form. So if you see this equation, so is it in the canonical SOP form? No. Even though there are 3 products are there which are added together, this is normally an SOP equation, but this is not in the canonical SOP equation, because if you count the number of variables here, there are totally 3 variables are there. ಯಾವ್ಯಾವು? A, B and C. But if you see the first 2 products, C is missing here, only A bar B is there, and in the second product A is missing, the literal A is missing here. If you get an equation, if you get an SOP equation where the product terms, if they include all the possible literals, ಅಂದ್ರೆ ಇಲ್ಲಿ C ಇದ್ದು ಇಲ್ಲಿ A ಇದ್ದಾರ, ಅವಾಗ ಇದನ್ನ ಏನಂತ ಕರಿತೀರಿ, canonical SOP equation ಅಂತ ಕರಿತೀರಿ. So since it is not in the standard canonical SOP equation, then we have to convert it into convert or we have to use some Boolean laws, we have to do some uh, uh, by hook or crook method, we have to convert it into a canonical SOP equation. How we shall see here. So a bar b plus b bar c bar plus abc. First we have to identify which term is missing here. In the first product, c is missing here. So simply we will write a bar b into 1. So anything into 1 will be equal to anything, that is a bar b anta barutte, doesn't make any effect. B bar c bar as it is bardvi into 1 doesn't make any effect. ABC we won't change anything in the last product because it includes all the literals, all the variables irodrinda, so we won't do any operation on the last product term. One can be written as c plus c bar. Why we have written c only? Because the term c is missing here, that's why one badli naವೇನ್ ಬರ್ದಿವಿ c plus c bar ಅಂತ ಬರ್ದಿವಿ. In case of second product, b bar c bar into 1, so since a is missing here, I can replace 1 with a plus a bar. I hope this concept is clear. Let's say if a literal is missing here, you have to write this equation according to the literal which is missing. So after that abc again it is untouched. Now we do an multiplication of the individual terms, that is a bar b c, which is the first term. Next a bar b into c bar, this is the second term. Then we'll do the multiplication here, a into b bar c bar, a bar into b bar c bar, again abc as it is written here. Now if you see this equation, I can call this as an canonical SOP equation because it consists of all the literals in their products. ನೋಡಬಹುದು ಇಲ್ಲಿ abc ಇರೋದು, ಇಲ್ಲಿ abc ಇರೋದು, ಇಲ್ಲಿ abc, ಇಲ್ಲಿ abc ಇರೋದು, ಇಲ್ಲಿ abc. None of the literals are missing in the products. I can refer this as an I can conclude this as a canonical SOP equation. Now we have to represent this using a min term representation. Min term representation ಅಂದ್ರೆ we have to write the decimal digit indications for the corresponding input combinations. ನೋಡಬಹುದು ಇಲ್ಲಿ a bar bc ಅಂದ್ರೆ 0 1 1. ಸೊ 0 1 1 ಅಂದ್ರೆ 3 ಅಂತ ಆಗುತ್ತೆ. ಸೊ 3 ಅಂತ ಬರೆದ್ವಿ ಇಲ್ಲಿ. ನೆಕ್ಸ್ಟ್ 0 1 0, that is 2. 1 0 0, 1 0 0 ಅಂದ್ರೆ 4. 0 0 0, that is 0 here. 1 1 1, that is 7. Now if you write it in the ascending order, ಏರಿಕೆ ಕ್ರಮದಲ್ಲಿ ಬರೆದ್ರೆ sigma m 0 2 3 4 7. So what are these actually 0 2 3 4 7? ನಾವು ಪ್ರಾಡಕ್ಟ್ಸ್ ಯಾವುದಕ್ಕೆ ಬರಿತೀವಿ, ಯಾವ ಕಾಂಬಿನೇಷನ್ಗೆ ಲಾಜಿಕ್ ಔಟ್ಪುಟ್ 1 ಇರುತ್ತೋ ಅದಕ್ಕೆ ನಾವು ಕರೆಸ್ಪಾಂಡಿಂಗ್ಲಿ ಏನು ಬರಿತೀವಿ, ಪ್ರಾಡಕ್ಟ್ಸ್ ನ ಬರೆದಿರ್ತೀವಿ, ಪ್ರಾಡಕ್ಟ್ ಇಕ್ವೇಶನ್ ನ ಬರೆದಿರ್ತೀವಿ. ಇಲ್ಲಿ ನೋಡಬಹುದು, ಇಫ್ ಯು ರೈಟ್ ಇಟ್ ಇನ್ ದ ಟ್ರೂತ್ ಟೇಬಲ್, so as we have already found that there are 3 variables abc and there is an output y. If you write the truth table with 3 input variables, I can have 8 different combinations which will range from 0 0 0 till 1 1 1. Now, so for which all input combinations am I supposed to write the output as 1? You can easily get to know by the min term representation. For the decimal digit or for the combination, decimal combination 0 ಅಂದ್ರೆ 0 0 0 ಗೆ output 1 ಇರುತ್ತೆ, first one. Next for the combination, decimal combination 2 ಅಂದ್ರೆ 0 1 0, ಅದಕ್ಕೂ ಕೂಡ output 1. Next 3 ಗೆ 0 1 1. Next 4 ಅಂದ್ರೆ 1 0 0, ಅದಕ್ಕೂ ಕೂಡ output 1. Next 7 ಗೆ 1 1 1 ಗೆ ಅದಕ್ಕೂ ಕೂಡ output 1. ಹಂಗಾರೆ ಉಳಿದಿದ್ದ ಕಾಂಬಿನೇಷನ್ಗೆಲ್ಲ ಏನಿರುತ್ತದೋ, ಸೊ ವಿಚ್ ಎವರ್ ಕಾಂಬಿನೇಷನ್ ದಟ್ ಈಸ್ ಮಿಸ್ಸಿಂಗ್ ಇಯರ್, obviously its value is considered as 0. ಅಂದ್ರೆ 0 0 1 1 0 1 and for 110 combination the output y will be 0. What is the third step? Third step ನಲ್ಲಿ ಹೇಳಿದಂಗೆ as per the min terms corresponding mux input is connected to VCC. ಅಂದ್ರೆ ಯಾವ್ಯಾವ ಒನ್ ಸಿನ್ಸ್ ಈ ಎ ಬಿ ಸಿ ನಾವೇನು ಮಾಡ್ತೀವಿ, ಸೊ ದಿಸ್ ಎ ಬಿ ಸಿ ನಂಬರ್ ಆಫ್ ಲಿಟರಲ್ಸ್ ಆರ್ 3. ಸೊ 3 ಸೆಲೆಕ್ಷನ್ ಲೈನ್ಸ್ ಇರುವಂತ ಮಕ್ಸ್ ಅಂದ್ರೆ ಯಾವುದು? 8:1 ಮಕ್ಸ್ ಆಲ್ರೆಡಿ ಕೊಟ್ಬಿಟ್ಟಿದ್ದಾರೆ ನಿಮ್ಗೆ ಅವರು. So these three inputs are mapped with the 3 selection lines of the 8:1 mux, and now these outputs are to be mapped with the inputs of the multiplexer. So ಯಾವ ತರ ಮ್ಯಾಪ್ ಮಾಡಬೇಕು ನೋಡ್ಬೋದು ಇಲ್ಲಿ 0 2 3 4 7 ಅಂದ್ರೆ 0 2 3 4 and 7. So for all these combinations the output is 1. So that's why all these inputs are connected to VCC. Clear? And the rest combination andre 0 0 1 means whichever that is missing here, 1 5 and 6. The 1 5 and 6, these three inputs are shorted together and they are connected to ground. So this is how a logic expression is implemented using multiplexer. I hope it is clear. Let's see another example. So y equal to a bar b bar c bar, a bar b bar c plus a bar b c. You have to use again an 8:1 mux because there are 3 literals are here. You can easily see this is already in the standard canonical SOP form, because since there are 3 products are there and the 3 products all of them they include the 3 literals. ಇಲ್ಲಿ ಕೂಡ 3 ABC ಇದಾವೆ, ಇಲ್ಲಿ ಕೂಡ ABC ಇದಾವೆ, ಇಲ್ಲಿ ಕೂಡ ABC. Doesn't matter whether it is available in the standard form or it is available in its complemented form. A ಇರಬಹುದು ಅಥವಾ A bar ಇರಬಹುದು, whatever, but whether the literal is present or not, that you have to look for. So ಇದು ಆಲ್ರೆಡಿ canonical SOP equation formula ಇರೋದ್ರಿಂದ, so no need to do the conversion to obtain the canonical SOP equation. So directly we will go for the second step, that is we will write the min term representation. So 0 0 0 that indicates 0, 0 0 1 means 1, 0 1 1 means 3. This is the canonical SOP equation and this is the min term representation. So as per this min term representation we will write the truth table for these 3 decimal combinations. Andre 0 1 and 3 ge the output is 1. 0 is indicated by the binary combination 0 0 0, 1 that is 0 0 1 and 3 na 0 1 1. For these 3 combinations the output y is 1. For rest all combinations the output is considered as 0. Then what is the next step? You have to map these 3 inputs with the select bits of the multiplexers. So A B C na idr jote multiply madidre idr jote map ಮಾಡ್ತೀರಾ. Next these outputs have to be mapped with the inputs of the multiplexers. ಯಾವ ಕಾಂಬಿನೇಷನ್ ನೋಡಬಹುದು? 0 1 and 3. The 0 1, this is 0, this is 1 and this is 3. All these 3 are connected to VCC, and whichever they are left andre 2 4 5 6 and 7. So these all are connected to ground. So this is how any logic expression can be implemented by following these steps. Okay, so this kind of an concept we will illustrate even in your lab also by doing the practicals. We will see in the practicals also. Next and the last concept is, so here we are going to list the different ICs. As I already told you, every combinational circuit or every combinational logic device will have its own IC. 16:1 mux, first we will list the multiplexer ICs. 74150, that is a 16:1 mux. 74151, that is 8 is to 1 mux. 153, that is dual 4 is to 1 mux, means there will be two 4 is to 1 muxes will be there in the single IC. And in 74157, quad 2 input multiplexer, means we will find 4 2 is to 1 muxes in the single IC, that is 74157. These all we will see in the laboratories. Next, demultiplexer ICs, a 74154, which is 1 is to 16 demux, and 74156, that is a dual 1 is to 4 demux. Dual in the sense 2 ಇರ್ತವೆ, quad ಅಂದ್ರೆ 4 ಇರ್ತವೆ. Next, decoder ICs, 74138, that is 3 is to 8 decoder. 74139, dual 2 is to 4 decoder, 2 is to 4 decoder ಇರ್ತವೆ. 7442, this is the BCD to decimal decoder. 7447, this is the BCD to 7 segment decoder. Then we will list as different encoder ICs as well. 74147, that is a decimal to BCD encoder, and 74148, that is an 8 input priority encoder. So we will be using all these ICs in our laboratories, and we will be doing the experiments to verify their functionalities according to the truth tables. So with this, by listing all these ICs, I am going to conclude the first chapter, that is introduction to the combinational logic circuits. You may expect a 25 marks question on this chapter. Thank you.